Welcome to Chapter 6, where we're going to start by talking about light as a wave. So we've talked about a lot of chemistry so far. We started with matter. We said that was made up of atoms. Atoms came together to come into compounds. Those compounds can change via reaction. We do a lot of that chemistry in solution. We learned how to predict those reactions. We also talked about using the heat associated with chemical reactions. So we have all of this kind of language as to how, we developed all the basic kind of language of what chemistry is. But there's something we very heavily glossed over, and that was the idea of what atoms are and how they come together to form compounds. We talked a little bit about ionic compounds, as the image there shows, but we just said covalent compounds are just more complicated and left it at that. So we want to spend some time to go into what exactly happens in that type of situation. Electrons are on the outsides of atoms. So if forming bonds and making compounds all about atoms coming together, when those atoms interact, it's going to be through their electrons. And electrons are not just randomly distributed around a nucleus. So far, we've just said they're in the electron cloud, kind of left it at that. But we have these image graphics, that kind of show there's rings or kind of paths of where the electrons are around an atom. And the arrangement of electrons on an atom are going to be what drive the chemistry, what determines what sorts of chemical reactions it does and with what other types of atoms. Before we get into talking about those electrons, though, we want to spend a little bit of time talking about electromagnetic radiation. And so electromagnetic radiation is just a really fancy way to say energy moving through space. There's a lot of different names for different varieties of electromagnetic radiation. They all fall into what we call a spectrum. So this electromagnetic radiation, there's a range of possible types, and they're all just kind of variations on the same thing. But they all have kind of different names. We may be familiar with X-rays or radio waves, microwaves, visible light. All of these are just different varieties of light. So we are going to call all of this light. These different names for these different categories are entirely artificial. They were invented by people. You can see there are just like hard lines drawn like right here for where microwaves start, just like boom, that's where the microwaves begin. And so, those sorts of ideas, these names are entirely artificial. These are all just types of light, and we can understand every single one of these as light. So light is generally described as a wave. When I say it's a wave, that means the idea is that this is energy moving through space, remember? So when the light is moving through space, there is a wave. So what that means is that the energy you can think of as going in like a positive and negative direction. So there's an oscillation to it. So as it moves along, you can see we go up and down, up and down. And there's this sort of kind of pattern to it, and it's periodic, right? That sort of repeating nature of the up and down. And so for this given wave, since light is a wave, we can characterize it using a couple different things. So we have amplitude, which we can see as the height of that wave, how kind of big the wave is. We'll see that's not actually very important for light. What is more important is wavelength. The symbol for wavelength is lambda. This is a lambda right here. This is a Greek lowercase l, so L for length, a lambda here. And this is the physical distance between peaks of the wave. So if you think about your wave is going up and then down, how far apart in space are those consecutive up peaks? And it's the same distance between the down peaks, so the wavelength would be the same. So the units for any wavelength are going to be distance units, and generally we use metric units. It can be any metric unit you want: meters, centimeters, kilometers. Obviously that'd be a pretty big wave if you're measuring it with kilometers, but those exist. Frequency is then the other primary characteristic of light, and frequency has the symbol of nu. So this is a new graphic image font here. It looks like a V. It's really kind of a swoopy V. Technically, it looks something like this. I've drawn it in a very exaggerated way, but it's this kind of swoopy V. It looks like that. When I write it in my hand, when like handwriting, how I designate this, because I can't, you saw how hard it is to draw that for me. I draw it as like a little V, and then I'm just going to put a little lip on it. So just like a little kind of pizzazz hanging off the side. So that's going to be for nu. This is Greek lowercase letter n. It's just what we use here for frequency. And frequency is the number of cycles of a wave in 1 second. So our units are going to be per second. So if you think about it, frequency is kind of how often. So how many times does the wave go by per second or in a second? This per second is technically what it is, but it's just named after someone, hertz. 1 hertz is the same thing as 1 per second. Right, 1 over s to the negative 1 power. That just means a fraction with s in the denominator. So if you have two waves that are traveling at the same speed, wavelength and frequency are inversely related. That means if one of those values is high, the other one is very low, or lower, right? That they kind of go in the opposite direction. So if you think about long wavelengths, so there's high distance between these two wavefronts. If you're traveling at this speed, you go up and down, up and down, right? We're moving along. We're not going up and down that frequently because it's a high distance between them. If we instead had a shorter wavelength, if we travel at the same speed, right, the same speed side by side, we just end up going up and down more frequently because the waves are shorter. So we're going up and down. So this is a relatively higher frequency because it is a shorter wavelength. So shorter wavelengths lead to higher frequencies. So if we take this and apply it back to the idea of light, all those different types of light that we referenced earlier are just different ranges of wavelength of light, because all types of light travel at the same speed, the speed of light. And the symbol for the speed of light is a lowercase c. And that speed is 3.0 times 10 to the 8th meters per second, so quite fast. Light does move very quickly. And so we then have all of these different ranges we have this huge range of potential wavelengths of light. They are inversely related to the frequencies. And so we can just take different kind of bins, different regions of wavelength and call those different names. And so to put all this together, then we can have the equation that c is equal to lambda times nu. The speed of light is the wavelength of that light times the frequency of the light. So because c is a constant, this number on the left side never changes. So over here, these two are multiplying together. As one gets bigger, the other one has to get smaller. So we can see you have something like gamma radiation up here, which has really small wavelengths and extremely high frequencies. Radio waves down on the other side have really long wavelengths, like meter to a kilometer wavelengths, and they have relatively lower frequencies. Light's still moving very fast, so it is still moving, it's still kicking pretty well, but you know, you're talking 1,000 to 10 to the 8th hertz. There is one portion of the electromagnetic radiation that is entirely random, and that is visible light. So wavelengths 400 to 700 nanometers are called visible light, and that is because that's what humans can see, right? Your eyes are tuned to seeing these wavelengths of light. So even though normally we think of light as things we can see, really a very small portion of electromagnetic radiation is visible to humans. Now, it's not a random portion, it is a very large amount of the light that comes from the sun is visible. That's why we can see it. And so 1 nanometer, or 400, 700 nanometers, that is quite a small wavelength. 1 nanometer, this is a metric unit. Nano is a prefix that means 10 to the negative 9th. That is 1 billionth of a meter. So rather short wavelengths of light, but 400 to 700 is what you can see. So let's look at an example of treating light as a wave. What is the frequency of a red light with a wavelength of 670 nanometers? We still want to start by asking, what do we want? Frequency of the light. What sort of information do we have? You can see we're given the wavelength of the light. And so we want to recognize that we can relate these with our light equations. Namely, we have C is equal to lambda times nu. Light is going to have a couple of equations that we're going to use, and it's going to be a matter of parsing out which one is the best equation to use for this particular application. In this case, since we want frequency and we have wavelength, it's going to be C equals lambda times nu. I want to know the frequency of a light. And so when we're looking at frequency, one of the things that we can always relate it to is going to be wavelength. So at the point in time when we're talking about light as a wave, these wave properties, we know that frequency and wavelength are going to be related. And they're related by our equation C is equal to lambda times nu. And so one of the biggest issues when we're working with light is kind of parsing out what these different variables all mean. And so frequency is going to be this sort of wavy V thing. That's my nu, that is my frequency. Lambda, that's Greek L, that is length, so that's my wavelength. And then C is the speed of light. So the speed of light is a constant. Wavelength and frequency are then variables which can vary, but are related by this equation. So what we want is frequency. Yep. So do we have the other things? You know, it's an equation. Do we have everything else? Wavelength is 670 nanometers. That's given to me right there. Speed of light then is not given in the problem, and that's okay because it's a constant. So we can look up what the speed of light is. It is 3.0 times 10 to the 8th meters per second. So we can go ahead and plug everything in. I have 3.0 times 10 to the 8th meters per second is equal to 670 nanometers times my frequency. So then frequency is equal to 3.0 times 10 to the 8th meters per second divided by 670 nanometers. And if I look at how this is written, I can see I'm going to have an issue. I have nanometers and meters. Those are different distance units and are not going to cancel out. So this is a frequent issue that comes up. Speed of light is always going to be in meters per second. Wavelengths are given in whatever units are most useful for that distance. So visible light is really short, so nanometers are the most useful unit. In order to get this to work, those units do need to be the same. So what I need to do is just switch out from 670 nanometers, which is a metric unit. So what I can do is that 1 nanometer is 1 times 10 to the negative 9 meters. That's just the definition of nanometer. And I get that it is 6.70 times 10 to the negative 7 meters. So I just need to do that conversion, get it cleaned up. Instead of using a nanometer representation, use a meter representation for everything. I can go ahead and plug that back in. This representation is the same distance, just a different unit. So 3.0 times 10 to the 8th meters per second divided by my 6.70 times 10 to the negative 7 meters. I can see now meter and meter cancel out, which is good. And if I do my arithmetic, I end up getting an answer. Nu is equal to 4.47 times 10 to the 14th 1/seconds. This 1/seconds is a totally acceptable frequency unit. It's a very common frequency unit that we see. That is, frequency is how often something happens, so per second. certainly does give us that. But this per seconds can just be rewritten Hz for hertz. And so we can rewrite this actually in a couple different ways, where we could get 4.47 times 10 to the 14th, instead of 1 over seconds, seconds to the -1 power. We know taking anything to the -1 power just puts it in the denominator of a fraction. We can also just, but those are like just different algebraic representations. We can also take the same number and just put in Hz. Hz honors Hertz, the scientist. It is a lot less clear, but Hertz is just the same thing as 1 over seconds. So this is the most frequent representation that you'd be told Hertz. That's just what people tend to use in these contexts. But it just means 1 over seconds. It has that exact same information in it. And we just want to know that we can do that translation.
Now it's your turn. Question 1 for participation 324. The end of the UV region of the electromagnetic spectrum occurs at 3.0 times 10 to the 16th Hertz. What is the wavelength of this light? This is the first question for participation 324, due Wednesday, March 24th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. The end of the UV region of the electromagnetic spectrum occurs at 3.0 times 10 to the 16th Hertz. What is the wavelength of this light?
So the one other aspect of waves that I mentioned earlier, but we haven't really talked about for light, is amplitude. This is the height of the wave. So generally, the energy of a wave depends on the amplitude of waves. Think of like water waves. Think of like a large water wave like say a tsunami. It's a huge wall of water. It's very powerful. It can move cars. Whereas smaller waves are not going to push this child over because they have a lot less energy. When you're dealing with general waves, amplitude is the determining factor for power. So with water waves, that's what we can look at. You know, that wall of water you can tell is going to have a lot of power to it. For light, this isn't the case though. If you take a piece of metal and you shine visible light on it, if you make that light brighter, right, you would think that it has a higher amplitude, there's more light, there was more power, it would be able to do more. But instead, if you shine this light on, say, a piece of metal, if you have red light, it does not matter how bright you make that light, nothing's ever going to happen. But for purple light, it doesn't matter how dim you make the light. When the light hits the surface of the metal, electrons come out of the metal. You can make the light as dim as possible, you just get fewer electrons. The brighter you make it, the more electrons you get. But it always happens with violet light. And with green light, same thing. You always get electrons coming out of the surface of the metal, but you're not getting the same, they're not coming out as fast. Okay, and so something unique is going on here when we're talking about light. It is behaving differently than we would expect with traditional waves. There's some sort of dependence on frequency when it comes to energy, which we'll have to talk about in the next video.
That's it. One video down, our first set for week 10 and for starting in on chapter 6, participation 324. We already found our first question. That's going to be due Wednesday. And then the midweek 10 homework on Thursday, we'll cover the same set of material. Second set of videos with the Friday participation, and then of course the weekly homework on Saturday. Emission spectroscopy lab will be due Sunday. That will only cover this first set of videos, so if you want to take a look at that. If you want to talk again about exam 2 performance, overall grade standing, happy to chat with you about that. Any of this content, how to do anything about the rest of the semester, really anything you want. Otherwise, we're just getting started here on chapter 6. See you in the next video.